Good morning. We're now going to look at a problem in Cartesian 3D vectors. This problem is actually the culmination of everything that we have studied so far in Cartesian 3D. Essentially, we have three mini problems which are put together and given as one large problem. And the idea is I'm given all the three concepts that we have studied so far. We have for a particular force the coordinate direction angles will be given. Then for another force we will be given the coordinate direction angle and one of the projection angles. And then for the third force we will have 2 points on its line of action given to us. And with all this information, I have to find the resultant force vector of these three forces in the Cartesian coordinate frame in 3D. And I also want to find out the coordinate direction angles of the resultant force vector eventually, and as well as its magnitude. Of course, I need to find its magnitude first before I go ahead and find the coordinate direction angles of the resultant. Alright, so here is the problem. I have the right hand rule for the Cartesian 3D system. So this is the z-axis, and then I have the x-axis, and then I have the y-axis. So positive x-axis, positive y-axis, positive z-axis. I'm going to extend the x and the y-axis along their negative senses. So here is the negative y-axis, and then I have the negative x-axis, which is going along here. Now I'm given three forces. The first force has a magnitude of 200 newtons and is drawn as shown. So this is the force F1. It has a magnitude of 200 newtons, and then two angles are given to us here. The angle that is given to us is a 60-degree angle right there, and then I'm also given a 45-degree angle right here. And you have to immediately notice that for this particular force, I'm given the angle made by the tail of this force vector with the positive z-axis. I'm given the angle made by the tail of this force vector with the positive x-axis, which means that I'm given two of the coordinate direction angles. And if I know two of the coordinate direction angles, then I know for sure that I can find out the third one using the identity that we have seen in lecture. Alright, I have another force vector F2, which I'm going to draw right here. So this is the force vector F2. F2 has a magnitude of 150 newtons. And the information given to us is one of the points on its line of action is the origin, which I'm going to call as O in a minute. And then there is also the coordinates of another point on its line of action given to us. So here is a point which we will call as the point A. I have the following dimensions given for the point A. So I'm going to drop down a perpendicular from the point A onto the XY plane, as you will see very soon. So I'm dropping down a perpendicular right there, and then I'm given three dimensions. The first dimension is a distance of 2 meters along the negative x-axis. So this is 2 meters. Then a distance of 4 meters along the positive y direction. This is 4 meters. I'm going to sneak that in here. And then a height, which I'm going to draw here. This height is also 4 meters. Alright, so for the point A, the location of point A, it is located at a distance of 2 meters along the negative x-axis. Now look at the negative x-axis drawn on this side. Then it's located at a distance of 4 meters along the positive y direction, and then 4 meters above the xy plane. And then I have the third force given to me. I'm going to extend the negative z direction right here. So this is the negative z direction. I have the third force which is given to me in the following manner. This force has a magnitude, which I'm going to call as F3, has a magnitude of 300 newtons, and the following information is given to us. An angle made by the tail of this force vector with the negative z-axis is given to us as 45 degrees. Notice that it's the angle made by the tail of the force vector F3 with the negative z-axis. So this means that there is a chance of us being able to obtain the coordinate direction angle about the z direction for the force vector F3, and then I take a perpendicular from the head of the force vector F3, I bring it up to the xy plane. So I'm going to do that this way here, right, and then I join it to the origin so that I get a nice 90-degree triangle here, and then I'm given one more angle, that is the projection made projection of this force vector F3 makes an angle of 30 degrees with the positive y direction. Okay, so this angle here is given to us as 30 degrees. Alright, so lots of information given in this problem. I am given a force vector F1, two angles 60 degrees and 45 degrees. Notice these are angles made by the tail of this vector with the positive z and the positive x direction. Then I have the force vector F2. I'm given 2 points on its line of action, coordinates of the origin, which is 0, 0, 0 in terms of meters or inches or feet, whatever you want to call the units as. We are going to stick with the SI system here because the force is in newtons. Then I'm given the coordinates of a point A on the line of action of the force. It's 2 meters along the negative x, 4 meters along the positive y, and then 4 meters along the positive z. And then a third force vector, which is F3 here, which has a magnitude of 300 newtons. And then it makes an angle, the tail of this vector F3 makes an angle of 45 degrees with a negative z, and then I take a projection from the head of this force vector F3, I go straight up onto the positive xy plane, and then I see that this projection here makes an angle of 30 degrees with the positive y direction. And the obvious questions are, I need to find the resultant force vector, and I also need to find out the coordinate direction angles of the resultant force vector. Okay, so we will write this out. So find the resultant force vector, which we will call as F suffix r, and then we will also find out the coordinate direction angles alpha r, and then beta r, and then gamma r. Alright, so these are the three things that we need to find apart from the force vector Fr. And essentially this means that I have to write the force vector Fr in terms of the Cartesian components along the x, y and z directions, and then go ahead and find out these three coordinate direction angles. Alright. So let's look at how we can proceed in this particular problem. So maybe just to write out what we need. So we need find Fr, which is the resultant force vector, and we also need to find out the coordinate direction angles of Fr. What are these, right? And these are essentially what we labeled as alpha r, beta r, and gamma r. And our aim is once we find all this information, we will draw the force vector F using the xyz coordinate frame and then mark all these angles just to be sure that we understand where they are located. What is the key idea here? So the key idea, as we have seen for resultant force vectors in 2D, Cartesian 2D, the same thing holds true in 3D as well. The resultant force vector is going to be the vector sum of the individual force vectors, which means that I want to write out each of these F1, F2 and F3 as Cartesian vectors. So write out F1, F2, F3 using the information given, and then find Fr. Alright, once again this is the vector sum, this is not the scalar sum. when we perform the vector sum, we take the I components of our f1, the I component of f2, the I component of f3, and algebraically add them up. Then we do the same thing for the j components of f1, f2 and f3, and then the k components of f1, f2 and f3, and that correspondingly gives us the x, y and z components of the resultant vector fr. Alright, so let's dig in and see what we can do in terms of a solution for this problem. Here is what I'm planning to do. I'm going to look at each of the forces, F1, F2 and F3 separately, and then I'm going to write each of them as Cartesian vectors and then eventually add them up. Alright, so let's take a look at the force vector F1 first. Right. So force vector F1. Now I'm going to redraw the x, y, z directions according to the right hand rule, x, y, and then the z axis. So this is positive x, positive y, and positive z, and then I'm going to extend the negative y direction. Then I have the force vector here, which is the force vector F1, whose magnitude is known to us as 200 newtons. So F1 is given to us as 200 newtons. Then two angles are given to us. I see that one of them is the 45-degree angle and the other is the 60-degree angle. So this is 60 degrees. Then this is 45 degrees. And then I can finally realize that if I'm looking for the third coordinate direction angle, then this has to be an obtuse angle based on the way the force F1 is constructed. Okay, so this is the third angle that I am seeking, which is going to be beta 1. Right, so this is what I want, and this angle here is going to be gamma 1, and this angle here is alpha 1. So from what is given to us, we know that alpha 1 is 45 degrees, beta 1 is unknown, gamma 1 is 60 degrees. How do I find out beta 1? I make use of the identity. And what is the identity? I have cos square alpha 1, cos square beta 1, cos square gamma 1 is equal to 1, and this means that cos square beta 1 is 1 minus cos square alpha 1, which is cos square of 60, minus cos square of gamma 1. Actually gamma 1 is 60 and alpha 1 is 45, as I have written here. It does not make a difference to us as long as we take them into account. Alright, and so once I see here cos square beta 1, cosine 60 is half, so cos square 60 is 1/4. Cosine 45 is 1 by root 2, so cos square of 45 is 1 by 2, which means that I'm going to get an answer of 1 by 4, which means cosine beta is either plus half or minus half, and I know that I'm looking for an obtuse angle, so this we know is going to be an obtuse angle. Based upon what? Based upon the information given that the force F1 has to be aligned in that particular direction, which means that this is not the answer I want, this is the answer I want. Cosine inverse of a half with a negative sign is nothing but 120 degrees. Alright, so we will write this out. So we see that, so we expect beta to be obtuse, which means that beta is going to be cos inverse of minus half from the previous page, or 120 degrees. Once I have beta, then all I have to do is write out the force vector F as a Cartesian vector. So I have F1 is going to be F1 cos alpha 1 in the I, F1 cos beta 1 in the j, F1 cos gamma 1 in the k. And I know the magnitude of the force vector F1 is 200 newtons. I know all the coordinate direction angles, and so I can fill this out. 200 times cosine of alpha 1 from the previous page was 45 degrees. Then I have 200 freshly found out cosine 120j, and then I have 200 cosine 60k. If I substitute and then find out the value, I get vector F1 to be the following. This is 200 cosine 45. I'm just going to leave it like that. So this is 200 by root 2 in the I direction. 200 cosine 120 is a minus half, so that's going to be minus 100 I j, I'm sorry, and then this is going to be plus 100k. 200 by root 2 is approximately 141.4, or the final answer for the force vector F1 is 141.4i minus 100j and then plus 100k. Do not forget the units, newtons. Alright, so we are done with the force vector F1. We have to look at force vectors F2 and F3 in the same way. F1 is the easiest of the lot because we know two of the coordinate direction angles, and we can find the third one using one of those canned identities that we have learned in class. Of course, we actually derived this identity, so there is nothing canned about it. We will look at the force vector F2 next. Now for the force vector F2, I'm going to redraw the situation. I know 2 points on its line of action, and this is harking back to what we had at the beginning of the problem. This is the positive x, positive y, and positive z direction. I'm going to extend the x direction along the negative side, and so positive x, positive y, positive z. I have the force vector right there, so this is the force vector F2, which is having a magnitude of 150 newtons. Then I know point O is the origin, I know point A, and we know from the information given to us that point A has the following coordinates. It's minus 2 meters along the x direction, then it's 4 meters along the y direction, and 4 meters along the z direction. Right? If I drop a perpendicular on here, you notice that this is the dimension given here. This is 2 meters. Of course, not drawn to scale. This is 4 meters, and then this height right here, which I'm going to draw. I know this is a slightly cluttered picture, but bear with me. This is also 4 meters. Then I know the coordinate of point O. Point O is the origin, so this is going to be 0, 0, and 0, so many meters. And if I write out the force vector F2, now F2 is going to be the magnitude times the unit vector along its line of action. And this unit vector along its line of action, as you can see here, this is going to be UF2, and UF2 you see is along the same direction as the unit vector from the point O to the point A, which means that I can write this as F2 times U from O to A, and this is nothing but the force vector F2 magnitude times the position vector from O to A divided by the magnitude of the position vector. So moral of the story, F2 is magnitude times the position vector by the magnitude of the position vector. And since I know the coordinates of point O and point A, I can find out the position vectors as well and the magnitude of the position vector. So filling those details out, we get to the following situation. So I have R OA as the coordinates of A minus the coordinates of O, and just as a case in point, coordinates of A were minus 2, 4, and 4. Coordinates of O were 0, 0, and 0. So coordinates of A minus O, so minus 2 minus 0 is minus 2i. Then I have 4 minus 0 is 4j, and then 4 minus 0 once again is 4k, so many meters. Magnitude of the position vector, square root of the sum of the squares of the components. The negative 2 doesn't make a difference to us, it becomes positive upon squaring. To the power 1 by 2, 4 square is 16, 16 times 2 is 32, 32 plus 4 is 36, square root of that is 6, which means that ROA magnitude is 6 meters. Alright, so now I can write out the force vector F2. Right, so F2 is going to be the magnitude of the force, which is 150, times the position vector, which is minus 2i, then 4j, and then 4k, divided by square root of 36, which is 6. Or if I write this out in its final glorified form, f2 is going to be 150 times minus 2 divided by 6, so that's minus 300 by 6 is minus 50. So that's minus 50i, and then 150 times 4 is 600 by 6 is plus 100j, and 150 times 4 is 600, once again divided by 6 is 100, so this is a 100k, so many newtons. Alright, so I have force vector F1, I have force vector F2, and the last tricky fellow here is the force vector F3. Slightly trickier because I'm not given all the information right off the bat, but I think based on what we have been given, we can easily find out what is to be found out, which is the force vector F3 in terms of its components. Alright, so look at the information. So we are now going to look at the force vector F3 next. Right, and I draw the x, y and z directions, the positive z, then I have the positive x, and then I have the positive y, and then I have the negative z direction, which is given to me here, and then I have the force vector F3, which is drawn here. So force vector F3 has a magnitude of 300 newtons, and two of the angles are given. One angle is the angle made with respect to the negative z direction, which is going to be 45 degrees, which means that the angle made by this force vector F3 with the positive z axis, as you can see, this angle here, this is going to be 180 minus 45, or this is equal to 135 degrees. Then one more angle is given to us, which is I take the force vector, I project it on the xy plane, right? Then I draw a line starting from the origin, and then I complete this triangle here. This is a 90-degree triangle right there, and then I know that this angle here is given to me as 30 degrees, and so if I can draw this component here, I'm going to call this component as F3 in the z direction, and I'm going to call this component here as F3 in the xy direction, and I'm going to focus my attention on this triangle, which I'm going to shade in blue here. Right, so if I look at that particular triangle, I first of all notice that okay, the force vector F3 is going to be in the negative z direction, and I know that if this angle is given to me as 45 degrees, and I know that if the angle there is 135 degrees, then the component of F3 in the z direction has to be a negative component. Alright, so I know from construction, based on what we have here, gamma 3 is 135 degrees, which means that F3z is F3 times cosine of gamma 3, and which automatically means that if I look at the force vector F3xy, then that's going to be F3 times sine of the angle here. If you look at this triangle here, this is also going to be a 45 degree triangle, so that's also 45 degrees, and so I can see that F3 xy is going to be F3 times sine of 45. Alright, so this automatically tells us that since I did not write it out as a negative F3z, I get the negative sign because gamma 3 is an obtuse angle. You can either write it out here, or you can eventually collect all the information and write out okay, F3z is in the negative z direction, as you can see from the arrow drawn here, and then say that okay, that has a negative sign attached to it. Alright, so in terms of taking the F3 xy component and splitting that into components along the x and the y axes, right, so I redraw the picture slightly. This is the z, the x, and the y direction, and I know that on this particular plane here, this is the xy plane, the angle that I'm given for the force vector F3xy is 30 degrees with respect to the y-axis. And so from the head of this force vector, if I draw lines parallel to the x and the y directions, you see here, and one more, if I can draw there, this is a 90-degree triangle, this is a 90-degree triangle. I see that this is going to be, if I call this as F3xy, this is going to be F3x, and then this creature here is going to be F3y. And the triangle that we are interested in is this triangle here, or the other triangle. It does not make a difference to us. And F3xy I already know from beforehand. F3xy is going to be F3 times sine 45. F3 was 300 newtons, which means that F3x is going to be F3xy, and you see that the 30-degree angle is here, so this is going to be sine 30, or this is going to be F3 sine 45 sine 30, and F3y is F3xy cosine 30, or this is F3 sine 45 times cosine of 30 degrees. So I have all the components for F3, so I'm going to write out F3 in its Cartesian form. So force vector F3, first of all F3x, which was F3 times sine 45 times sine 30, so this is going to be 300 times sine 45 times sine 30. F3y was 300 sine 45 times cosine 30, and this will be 106.1 so many newtons. This will be 183.7 so many newtons, and F3z. Now you want to be careful here. You could either write this as F3 times cosine of 135, and this indicates that it's already taken to be in the negative z direction. Already says right. If not, you can say that this is F3 times cosine 45 and then put a negative sign eventually. F3 is 300, cosine 135 is 1 by root 2, so this is around 212.1 newtons. The negative sign will be taken care of right here. And so if I write out the force vector F3, this is going to be F3xi, F3yj, F3zk, or force vector F3 is 106.1i, 183.7j, minus 212.1 k so many newtons. Alright, so we have all the three force vectors F1, F2 and F3, and it is now time to write them all out, add them up, and then call it a day. Alright, so here are the three force vectors. I'm just going to rewrite F1, F2 and F3. So force vector F1 from before was 141.4i minus 100j plus 100k, so many newtons. I'm going to skip the fact that these are newtons, or well, let me as well write it out here. And then F2 was a minus 50i, then I had a plus 100j, and then a plus 100k, so many newtons. F3, just found out right now, is 106.1i, 183.7j, minus 212.1k, so many newtons. Key idea: resultant force vector is the vector sum of the individual force vectors, which means Fr is going to be the following. I take all the I components, 141.4, then I have a minus 50, then I have a plus 106.1. All of these are in the I direction. Then I do the same thing in the J direction. I have a minus 100 from F1, I have a plus 100 from F2, and then I have a plus 183.7 from F3, and then I have the K components. I have a 100 from F1, a 100 from F2, and then a minus 212.1 from F3, and all of these are in newtons. And all I'm left to do is add these things up, which is our next step. Alright, so eventually after adding all these up, I get Fr to be the following. It's 197.5 in the I direction, 183.7 in the J direction, and a very small component in the K direction. It's 12.1 K, so many newtons. This is the Cartesian form of Fr. Square root of the sum of the squares will give me the magnitude of Fr. So magnitude of Fr is 197.5 square, 183.7 square, minus plus 12.1 square, 4 to the power 1 by 2. And so Fr has a magnitude approximately equal to 270 newtons. So this is the last step in this problem, is to find the coordinate direction angles and preferably draw out the force vector Fr. So let's do that. We have formed out the force vector Fr. We have its magnitude as well. The first thing I'm going to write out is the standard form of the resultant force vector in terms of its coordinate direction angles. So I have the standard form. Fr is Fr cos alpha r in the I, Fr cos beta r in the J, Fr cos gamma r in the K. I also have from the previous page Fr as 197.5i, 183.7j, and a minus 12.1k. And furthermore, magnitude of Fr was approximately 270 newtons. And in order to find out alpha r, beta r, and gamma r, all I have to do is take this guy, and equate them. Do the same thing here to find out beta r. Do the same thing here. Include the negative sign. Sometimes I write it out as this, just to ensure that I take the negative sign into consideration. I know the magnitude of Fr, so I can write out the answers. Alpha r is cos inverse of 197.5 by 270. This is an acute angle. This is going to be approximately 43 degrees. Beta r is cos inverse of 183.7 divided by 270. This is going to be slightly larger than alpha, 47 degrees. And then gamma r, be careful here, don't forget the negative sign, and this is an obtuse angle. Any angle greater than 90 degrees, 92.6 degrees. So we have alpha, beta, and gamma for the resultant force vectors. And now the final thing to do is to actually draw out the force vector and then mark these angles accordingly. So we have alpha r is 43 degrees, beta r is approximately 47 degrees, gamma r is approximately 93 degrees, 92.6, approximately 93 degrees. And so if I draw the force vectors, I have the positive z-axis, positive x-axis, positive y-axis, so x, y, and z. I'm going to draw the negative z direction right there. And so I know for sure that the angle made by the resultant force with the z-axis, which is gamma r, is an obtuse angle, and I know that the angles made with respect to the x and the y are acute angle, which means that the force vector Fr is going to be in the following direction or the following sense. So this is going to be Fr, where I see that the angle made, this is drawn in an exaggerated sense, this is gamma r, which is the 93 degree obtuse angle. Then I also have the angle made with the tail of this force vector with the positive y direction, this is going to be beta r, and then the angle made with respect to the positive x-axis is alpha r, and both alpha r and beta r, these are acute angles, but then this guy is an obtuse angle. And this makes perfect sense because the component of Fr in the z direction is going to be negative. It's a small one, but it is still going to be negative. This is shown in an exaggerated sense here. Okay, so this is exaggerated here, this gamma r, which I'm not going to write out. And then the other two we know from construction is both positive components along the x and the y, and as a result these are acute angles. Alright, so in summary, what we've seen so far is the following. I start off at the first page of this problem. In the first page of the problem we are given three forces. I have a force F1, I have a force F2, I have a force F3. Magnitudes of each of these forces are given. For the force F1, two of the coordinate direction angles are given. For the force F2, 2 points on its line of action are given to us. For the force F3, one of the coordinate direction angles, of course the complementary, the supplementary to this one, is given to us, and then one of the projection angles, 30 degrees, is given to us. And the question asks us to find out, okay, what is Fr, written as a Cartesian vector, find its magnitude, and then find its coordinate direction angles. And we went through, break each of these forces F1, F2, F3 into their Cartesian components, add them up respectively, and then eventually club them all together, find out Fr, and then we find out alpha, beta and gamma r for the resultant, and then we draw the final picture. Thank you.